Hello and welcome to today's ACM Learning webinar. This webcast is a part of ACM's commitment to lifelong learning and serving the over 97,000 computing professionals and students who are ACM's members. I'm Victor Klang, Deputy CTO at Lightbend, and you can find more info on my background in the bio widget on your screen. For those of you who may be unfamiliar with the ACM or what it has to offer, here's more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. You can see some more of the highlights on your screen. The ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides timely computing information published by the ACM, including Communications of the ACM and Q magazines. Access to the ACM Digital Library, the world's most comprehensive database of computing literature, international conferences that draw leading experts on a broad spectrum of computing topics, and support for education and research, including curriculum development, teacher training, and the ACM Turing and ACM Prize in Computing Awards. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you will find a number of additional widgets and resources. If you're experiencing problems with the slides or audio, press the F5 keys if you're on Windows, Command+R if you're on a Mac, or refresh your browser on a mobile device. Or you can close and relaunch the presentation. To control the volume, adjust the master volume on your computer. And if you have any questions during this webinar, please type them into the Q&A box at any time during the webinar and click the Submit button. I'll organize the questions as Jonas Bonér speaks, and he'll receive time at the end of the presentation to address them. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available, and check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a minute to fill it out to help us improve our webinars. You may also open the link to the survey at any time from the resources window on your screen. You can also use the Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag ACMLearning. Be watching for your tweets. We also have a new community discourse page to continue the discussion after this webcast, including questions we won't be able to get through during the Q&A session. Now, today's presentation is Reactive Microsystems, the Evolution of Microservices at Scale by Jonas Bonér. Jonas Bonér is the founder and CTO of Lightbend, inventor of the Akka project, initiator and co-author of the Reactive Manifesto, and Java champion. He is also an ACM case study contributor, and you can find this case study on the use of reactive systems at Hootsuite in the resources widget on your screen. Jonas, without further ado, take it away.
Thank you, Victor. So, since I've already been introduced, let's dive in to the content of this presentation. I don't think it comes to as any surprise when I state that microservices are very hyped today, and I would say it is mainly for a good reason. You know, we are pop culture, and we get excited about things, and you know, if one of us runs, all of us runs. So sure, I mean, it's not always for good, but I'll say that microservices are hyped today at this point in our industry's time for a reason, and that is that it can really help us to scale the organization. it has proven to be great as a way to sort of modernize architectures, to sort of deliver software faster. I mean, shorter time to market, since it allows us, to sort of scale the organization by having autonomous teams sort of building and shipping and sort of upgrading and rolling out features fully independent of each other, sort of not getting in each other's way. Something that we have sort of been almost used to do when we've almost been used to sort of the opposite of that when we're building systems with a monolith, where each team has to sort of upgrade their software in lockstep with all the other ones. The problem, though, is that there is a lot of confusion about what really constitutes a microservice in itself, but also what is microservices-based architecture is really all about. And so let's say that a company want to modernize their legacy monolith here, and it might look something similar to the picture in this presentation here. The problem is that way too often companies move towards an architecture like this and settle for that. This is what I call an architecture of microliths, where you sort of have turned your regular method calls into blocking RPC calls. Now the only thing you really gain by doing that is now you have even higher latency between the requests between the services, and often these microliths still have blocking the database calls down to sometimes even a single database with a single schema. So it looks like it's microservices, but we sort of drags along a whole pile of problems that we have with monoliths. And I think the main problem here is that we still maintain this strong coupling between the services, and this means that we are unable to take full advantage of the promise of microservices and also the promise of the cloud, and that actually microservices can be a perfect fit for if we just do the architecture right. So the microlith can be sort of defined as single instance microservices communicating over blocking protocols, and the problem with a single thing is that it can't possibly be resilient. You need redundancy in order to have resilience. And the same thing, it can't be scalable, sort of by definition, because you need more than one thing in order to achieve scale. So this makes it really hard to sort of take advantage of the promise of cloud computing, where you sort of pay as you go and sort of scale up and scale down depending on how the application is being used, etc. And I believe that event-driven architecture can really be sort of one of the keys in order to fully take advantage of the promise of microservice, and we're sort of helping sort of putting it and becoming real about putting it into its true context, which is actually distributed systems. According to Gartner, the definition of event-driven architecture is that an event-driven architecture is a design paradigm in which a software component execute in response to receiving one or more event notifications. So event-driven architecture can sort of work as an intermediary, and it sort of introduces this decoupling that we really need and allows us to have fully autonomous components that can be sort of built and delivered by autonomous teams, as I've already talked about. So event-driven architecture can really help us break down the chains of legacy software, so that is holding you back as an organization, and can really help us to reduce the risk by orders of magnitude, at least in my experience. So the first question might be then, what is an event? A lot of people talk about events nowadays, and event is really hyped. I think events, it's one of the most fundamental things is that events is really all about facts and information. They represent facts that are immutable. Facts are always immutable, but events represent immutable facts. And knowledge as a concept can only grow. You can only add more knowledge. I mean, that's how we all evolve as humans. That's how we learn from being a toddler up to an adult, etc. And this means that facts can only accrue. You can only add facts. So this means that facts can, as they enter a system, I mean, you as an individual, when you learn things and hear things, etc., can be disregarded or ignored. I mean, we might assume, have the right to assume that the sender or the guy actually lies for some reason, or that we have the facts that arrive to us sort of are conflicting with other facts that we have accepted for being the truth. So that is okay, I believe. But the thing is that once we have accepted a fact, it can't be retracted. It is a fact that we sort of have taken on as being the truth. And this means that facts also cannot be deleted. I mean, sometimes we might wish that we actually could undo certain things or unhear or unlearn certain things, right? But it is a fact, no pun intended, that if we have accepted the fact, we better live with it. It can't be deleted, even though in computer science, etc. There might be actually a need to delete it for legal or for moral reasons. I won't go into detail about that, but as a concept, I believe that facts can't be retracted and they can't be deleted. However, facts can invalidate existing facts, meaning that new facts that enter the system can then invalidate what we know for being true naturally. I mean, that's how we learn and sort of, about the world all the time around us, right? And I think software components should really behave the same. Event-driven services, though, what are those? I believe that they receive and react or do not react, if we choose to ignore the facts, to facts that are coming its way. And then we can choose to sort of react to these facts by doing some sort of processing or whatever. And once we're done, we sort of publish new facts then as event to the rest of the world to react to and to listen into if they are interested. And the interesting thing with this way of working with facts that sort of just enters, that we can subscribe to, is that it tends to sort of invert the control flow of the system, and that can really have profound implications of minimizing the coupling and also increase the autonomy of the system as a whole. Another very important thing that's sort of hyped today is reactive. People talk about reactive programming and reactive systems, etc. This image is taken from the Reactive Manifesto that sort of explains what it means to build reactive systems and sort of outline the three sort of core different traits: being elastic, being resilient, and being responsive, and how all that can be achieved by basing the architecture on a message-driven core. I believe also that microservices built in this type of fashion, with basing it on the core reactive principles, have a much higher likelihood of sort of fully embracing the promise of cloud computing, yet again, being fully elastic and scale on demand, being responsive as sort of the load goes up, and, being able to sort of shrink the amount of resources that are needed as the load goes down, both equally important, to preserve energy and preserve cost. And the same thing, being elastic. Customers today are extremely picky, and they usually don't accept much downtime. And the promise of the cloud is that we can quite cheaply have redundancy. But then are being able to fail over to other nodes that can continue the processing. So in a way being responsive in the face of failure. So I think both of these are extremely important to sort of take with us as core principles. I won't go into detail exactly how you will build such systems, in this talk, but I think if you haven't read the Reactive Manifesto and studied the reactive principles, I really encourage you to do so. So one of the underpinnings, in the reactive way of thinking is that you need to go async, that you should never really block. Async and non-blocking execution and I/O is often a lot more cost efficient and more since it allows more efficient use of the resources that are available. It also can really help us sort of minimize the contention in the system. So the contention on the resources that are high, in high demand, so to speak. And contention in general is one of the biggest hurdles to scalability, to low latency, and to throughput in general. It's also extremely important, alongside of being async, that to always apply back pressure to the system, and or someone will get hurt. The question is then, what is flow control really all about? Yeah, it's really that a fast system can't overload a slower system. And so this is sort of a little illustration that I found somewhere on Twitter some time ago in a completely different context, but it really shows, illustrates quite well the need for something like back pressure to hint, that the slower consumer here can't possibly keep up. So what's needed is sort of a continuous feedback channel where the slower consumer can sort of hint to the producer if it should sort of slow down, or if it doesn't have much work to do, actually hint that it can speed up. And what's really needed here is that all parties sort of collaborate in order to make this flow control, or this the pace of the flow throwing downstream be as optimal as possible. Another really important thing is that microservices, they are often sort of looked as individual entities, and people talk about how you can best implement one single microservice. And there are like scaffolding frameworks that makes it very easy to do so, etc. But I'd say that is just the starting point, because microservices, they really come in systems. You can't look at them individually and make sense of them in isolation. They really collaborate, and work together in order to solve problems. And it's actually in the space in between microservices that most of the hard things are around microservices, because that is when we enter the space of distributed systems, which I'll talk more about in a second. But then to have all these microservices communicate, a great way of doing that is to use the event stream as a way to sort of integrate all these components, subsystems, services, etc. So I'll try to illustrate what I mean here. Let's say that we have one guy here, some sort of user that then sends a command to a service here. And this service might have some sort of queue, then a mailbox, and once the command is sort of picked up, it is somehow processed. That will then cause an event to be created. That sort of represent the fact that this action was sort of performed, and it is sort of then sort of pushed out in an asynchronous fashion to the event stream, the event bus in the system. So then this event bus then can choose to relay this event to whoever might be interested to listen in to what happened in this service, where the event, that the event that it represents, sort of the action that the event represent happened. So this event, might end up in some queue here, and then sort of then put on for some sort of processing in other types of services. But what's also interesting is that it doesn't have to be other services that sort of reacts to this event, because it can also be, for example, databases that sort of consumes events for some sort of event logging techniques, for audit reasons, for integration with other systems that might be done through the database, or communicating through some sort of external system that might be interested in that. So the event stream can really work as a sort of an integration fabric between anyone that might be listening in or interested in what's going on in the system, being services, being databases, SQL, NoSQL databases, being stream processing frameworks, pushing it down to HDFS, etc., or external systems that is sort of outside our scope. And what's really interesting or really important to understand is that here, eventual consistency really rules the game. Since everything's happening in an asynchronous fashion, we really need to fully sort of embrace eventual consistency, which can have huge implications on our design of our systems. It is a fact that eventual consistency is actually quite hard. It's harder to understand and harder to reason about than strong consistency. But we as developers have sort of been spoiled by strong consistency. One single, globally consistent now, when we can always assume that everyone else, sort of immediately knows exactly, sort of assumes the same world as I do. There's always, acid, strong consistency, atomicity, etc. However, the world usually don't work like that. And I think if we need to model the world, effectively at scale, I think we need to actually embrace the fact that this is not how the world operates. One fact is that information travels at the speed of light. This puts a limit at the speed of information. This means that information, the transfer of information, actually has latency, and it might sound like sort of an obscure sort of fact that might not be of much relevance for you today, but it is actually a fact in most computer science systems, most software systems today. That it is actually, the speed of light is a hard limitation that needs to be taken into account. And so in general, this means that information is always from the past. That's really true for everything that we observe. Is that when you do observe something, hear something, sort of feel something, see something, it's often already happened, often quite some time ago. So in a way, we're sort of always looking into the past. Sort of, experience is always in the eye of the beholder. So that means that our experience of the present and now is actually relative. Others might not have the same experience, which is also something that we need to take into account. And and as soon as we exit this boundary of the service that we talked about, these event-driven services, we actually enter a wild ocean of non-determinism, and that is the world that we call distributed systems. And it's the world where systems fail in the most spectacular ways. Where information can get lost, where information can get reordered, or even garbled, messed up, and also where failure detection is a guessing game. And this might sort of sound terrifying, but it's actually also the world, even though it is scary, it's actually the world that gives us solutions for things like resilience, elasticity, isolation, and etc. Simply because it gives us more knobs to turn, and by being sort of more true to how the world actually works, I'd say. But it's really, really important in order to sort of stay sane, modeling this type of systems, that we fully embrace the inherent uncertainty of the system, and that we model this uncertainty. And this uncertainty really is the space in between the services. Pat Tellen once said that in a system which cannot count on distributed transaction, meaning strong consistency, the management of uncertainty must be implemented in the business logic. So it's really up to you as a developer to manage this in your own code, in the semantics, and how you design and model the systems. And in order to do that, I think it's extremely important that we don't try to hide the uncertainty, but instead we need to make it explicit. It needs to be part of the programming model, and it's really all about making the network and the failure modes of the network and the failure modes of distributed computing first class in the design of our systems. And we really need to sort of, as I said before, exploit the reality in our design and to start using that, as our advantage, instead of trying to fight it through, like we used to do so many times in the past, through distributed objects, trying to fake that everything looks local, like RPC, or try to fake that every distributed, invocation is local. Ignoring things like partial failures and all the the madness that can go on by actually making a distributed method invocation, etc. And I believe that events actually can lead to greater certainty. And the reason is essentially that events can help us to sort of craft these this fully autonomous islands, in this vast, sea or ocean of non-determinism. And within these islands, we can actually sort of live happily under the illusion that the time is absolute, that there is just one single present, and that the world is deterministic, even though it's not. So it's sort of an escape route out from this, scary wild ocean of non-determinism that goes on, in the space between these safe islands, so to speak. But in order to do this, I believe that the mutable state needs to be contained. I talked a lot about facts, and facts are immutable, and etc. But I think mutable state actually has its place, but it needs to be non-observable to the rest of the world, fully contained on our sort of isolated island of determinism, so to speak, fully contained in a safe haven, and can only be used for local computations. Once you're done with the processing and you're ready to tell the world about your results, then you publish immutable values representing what you came up with, as facts out to the rest of the world. And that's often done by sort of emitting events, that sort of encapsulate this fact, sort of this insight or whatever that you came up with within your component. And this means that other components, other services, etc., can sort of base their reasoning on stable values instead of guessing, what's going on, or worrying that you might retract a certain fact or something. And so microservices really come in systems. But what is less clear, and what I really believe is as true, is that microservices also come as systems. And what I mean by that is that each microservice really needs to be designed as a distributed system by itself. All parts in the microservice need to be considered as part of the system. So this is what I mean when I talk about microsystems, that microservices are really small systems in itself, where you might, for example, as in this image here, you might have a stateless service layer, you might have an entity sort of aggregate persistence layer, you might have a service gateway that's a routing between all of these sort of instances for load balancing. You might have an anti-corruption layer, you might have service discovery, authentication, security. Even the client, can sometimes be helpful to see, as part of the system. Sometimes not, but my point is here is that a microservice really consists of all these moving parts, and to really make sense and to be able to sort of make promises to the world about the semantics and the promises what actually can hold from within the microservice in terms of contracts really require you to take all these pieces into account. So what we want is really event-driven microservices, and if I try to illustrate sort of the way I view the world here and how it relates to reactive systems, is that if you have the network boundary here and sort of have the sort of ladder of abstractions going up, then if you have one client here sort of want to communicate with another, some user somehow, then the ideal way is to do that through some sort of unified abstraction. It can be like event-driven microservices using pub/sub or point-to-point or streaming or something like that. Then it sort of publishes one event to this layer. Then that sort of event is sort of usually relayed to a local event loop that does sort of some sort of queue that does sort of processing, and then sort of relays that to the distribution fabric. And the distribution fabric uses message passing then to relay that across this network boundary over to other nodes. Then the distribution fabric then sort of passes up this event over to the local event loop on the other side, and then over to this unified abstraction of in this case event-driven microservices. Or it can be some sort of Kafka-based message broker or similar. And then finally, the event sort of is relayed to the user that did subscribe to it. So the beauty here is that this gives us a way of having the reactive systems and the principles of reactive systems for doing the heavy lifting. You know, all these hard things that we talked about. You know, that relates to distributed systems. I mean, the reactive systems here in the distribution fabric thing can make the guarantees, you know, about resilience, scalability, delivery guarantees, you know, do things like retries, idempotency, deduplication, things like that, and sort of make sure that the latencies are kept within the SLAs, while sort of the user can still benefit of the simpler programming model of event-driven microservice or of the streaming abstractions or a general sort of reactive programming type of semantics. So this is the way I view it, and if you look at it like that, then sort of basing it on a platform that sort of is implemented using the reactive principles, like for example Akka, means that you know you can sort of delegate a lot of these hard things to the underlying fabric. In this case, Akka. And sort of focusing on building business value instead of the hard things around distributed systems. So in general, I mean, I think as I said before that you need to design, you know, your system around these ideas, around sort of embracing uncertainty and the boundaries, you know, where you can actually be certain about something and live in a world of more determinism, etc. And one tool that sort of helped me a lot with this is what is called event-first domain-driven design. I'm sure you've heard about domain-driven designs, or DDD. And that's a great tool that served us well in the last 15 years. But you know, if you just use it blindly in this sort of new world of microservices, it can actually lead us down the wrong path, I believe, because the problem is sort of that it sometimes puts focus on the domain objects too early. It puts focus on structure in the design too early in the design process. And you know, Greg Young once said that when you start modeling events, it forces you to think about the behavior of the system as opposed to thinking about the structure of the system. So what you really should do is that you should not focus on the things, the nonce that we've been used to do, you know, the domain objects, try to understand them and mine them. Instead, we should focus on what happens in the system, try to find the verbs, because that will lead to our events in the system. So let the verbs and the events drive the design, and then eventually, we need to sort of come up with what are the domain objects, but we should not start there. And instead, we should sort of, just like a detective coming into a crime scene, we should sort of try to mine them, ask ourselves what are the facts. And one technique that's sort of proven to work quite well here is a technique called event storming, in which we sort of bring in all the stakeholders, all the domain experts, the programmers, etc., in one single room, and have them brainstorm using post-it notes. So the exercise is all about them trying to find the domain language and the semantics, you know, of the domain through the events. Try to understand how data flows, who's talking to who. What event is causally related to another event, etc. And what we're trying to do here in this process is to understand sort of two things: intents and facts. First, intents are usually sort of hints for intent, so to speak, can be communication, conversations, expectations that you know one part of the system might have on others, contracts between different parties of the system, or things like transfer of control. Well, facts, you know, can usually be mined by looking at things like state, history, causality, notifications, and transfer of state. And often, you know, commands are, you know, what we then or is what is coming out of the intents, while the facts are usually represented by events. And so if we try to understand then, so the semantics of commands and events a little bit better here, you know, commands is sort of the object form of a method or an action request, you know, and that should be phrased in the imperative. Like, for example, create order, ship product, etc. And commands usually sort of causes side effects. the reactions in the components that receive the commands. And these reactions then sort of are represented as events, in a fact that something has already happened. And that is usually phrased in past tense. So order created instead of create order, and product shipped instead of ship product, etc. But if we sort of try to dig a little bit deeper here, then commands is really all about intent, while events are intentless. And commands are directed, while events are anonymous. Commands, they have a single addressable destination, while events, they just happen for others. Can be 0, can be 10, can be 100 to observe. Okay, and so this means that commands actually model personal point-to-point communication, while events sort of model broadcast. Thinking that speaker's corner, where you stand on a box and sort of shout out your views. Someone might be listening in, someone might not. Whoever receives a message, that's nothing that you can control really. So and also commands, since they model personal communication, that means that they actually do have distributed focus because they actually cross boundaries, they cross contexts, while events, they have just they only have a local focus, which is actually the need for having the local event loop hooked up with the distribution fabric to relay these events across nodes if needed, using communication. And commands is really all about command and control, while events is all about autonomy. So I think, both are equally important, I'd say. Normally, I'd usually try to mine the events and rely on events as much as possible, because it can really lead to better autonomy, but sometimes commands are absolutely needed. And I really believe that we should sort of let the design of events and also commands sort of define the bounded context, help us to define the protocols that we, and also the promises that we can sort of publish to the world, that we can hold, so to speak. So the question now is then, are we done now? And perhaps, I think by just sort of embracing sort of full events first domain-driven design, by relying heavily, not exclusively, but heavily on the event stream as an integration unibus for communication, for relaying events and commands, I think we can actually get quite far. But it's also, but to some extent, we might actually miss out on some of the best parts, because events can also be used for things like persistence and for managing time. So even though this is a little bit more of a advanced concept, I still feel that it could be worth to go through to give you a glimpse of what can be possible by fully go all in on a fully event-driven architecture, even for persistence. So the event-based persistence, and if we're going to dive into that topic, so Jim Gray once said that update in place strikes system designers as the cardinal sin. It violates traditional accounting practices that's been observed for hundreds of years. The problem here is update in place. And I think, yet again, we should, in order to solve this problem and sort of escape, the curse of update in place, we should really sort of yet again sort of learn from the real world. And I think we need to sort of relearn basic accounting principles, just like Jim Gray says here. We have, in order to do so, we might have a lot of unlearning to do, because it might feel unnatural to look at the world like this. But I think it can absolutely be worth it. So it can really be helpful to sort of rely on fundamental practices of traditional bookkeeping. And think about, our design through the concepts of event logging, where we sort of store each event in the order they arrive, durable on disk, just like transactions, in transactional systems, and just transactions in a ledger if you use traditional bookkeeping. And if we do it like this, then I believe that event log can really be the bedrock on which we can build a lot of things like consistency, actually strong consistency, because there is strong consistency within the single event log, including availability, scalability, and traceability, full audit, into what's going on into the system for debuggability and things like that. Pat Helen once said that, the truth is the log. The database is a cache of a subset of the log. It used to be a reason to use in-place updates. Disk space used to be very, very expensive. But the thing is that today it's incredibly cheap. So I don't think there's any reason to not store all, or at least, more or less all history forever that's ever happened in the system. The question is, why should you settle for working with a cache of a subset of the real thing when we can actually use a log directly? So I think we should really embrace the log as sort of a core building block in our design. The interesting thing is that the log is not just a database of the past. It's not just a database of the present, like most SQL databases are. They just give you a snapshot in time for how the world looks just now, through ACID, atomicity, and isolation, all these things. But actually, it can be a database of the past where you store everything that's ever happened in the system. You have full traceability, and a pattern that is it's really great to achieve that sits on top of the concept of the event log is a pattern called event sourcing. And I really believe that could be the cure for the cardinal sin that Jim Gray talked about, in actually solving the problem of updating in place. And it works the way that you log every state-changing event to a component in order as they are created. And the interesting thing is that if you design your system as being fully event-driven, then you normally have all these events already in the system, and they enter your component in order, and you perform the side effect, fully atomic within the component in the order as the events or the commands arrive. So the only thing you actually need to do is to materialize them on disk, store them durably, not just having your queue to your event-driven component being ephemeral in memory, but actually having it backed by a durable queue in some sort of database. It can be a SQL database, can be Cassandra, SQL database, or it can be, sort of a specifically, written event log, that only does that. And the interesting thing here is if you sort of back the aggregate with an event log, then you have strong consistency within the aggregate, and can still rely on eventual consistency for things like scale, resilience, and so on between the aggregates. So, an illustration I try to illustrate sort of the main points here is that, let's say that you first want to walk through the happy path. As then commands enter the system, we receive them, we verify them. Let's say that is an approved payment command. Then we create a new event representing, the approval of this payment. Let's call it payment approved. Then we append that to our event log on durable disk. Once we've done that, and if that's done successfully, then we know, for a fact that's stored, we can relax. Then we can update the internal component state in memory. And then we can run the side effects, sending events or commands to other services, sort of launch the nukes, so to speak. In this case, approve the actual payment by sending it downstream, to some sort of Visa service or PayPal or whatever. Then in the sad path here, that means when something has gone wrong and we want to recover from failure, the only thing we need to do then is rehydrate the events from the event log. So replay them, bringing the component up to speed, and by sort of updating the internal component state. And the beauty here is that this means that we can sort of persist, state in memory, so to speak. And Martin Fowler calls this pattern memory image. You can look it up later if you want to read up more on this. So some of the benefits of using these techniques is that we have one single source of truth. We have all the history that's ever happened for that component stored on disk. And as I said before, it allows for this memory image by having durable in-memory state, which can be extremely powerful because it sort of avoids, this classic problem with this object relational impedance mismatch, where we have to map your object in memory to some sort of relational table on disk, through some OR mapping, etc. Right? And we all know that OR mapping, is a root of all evils. I've spent way too much time trying to resolve, problems that are more than less, or often less than intuitive in Hibernate, etc. And you can really sort of go all in on the sort of optimal representation in memory, and just use that, not having to worry about how it's actually stored on disk, because that's just taken care of by the event log. It also allows others to sort of subscribe to these state changes. They can be actually a subscriber to this event log on disk. Others might be interested in listening in how your component state evolves over time. And it also gives us usually a great mechanical sympathy, as Martin Thompson usually calls it, by sort of being aligned with how modern hardware design actually works. Things like single writer principle, having one single writer writing every event, sort of using append only logging in sequence. Of course, there are always disadvantages as well, and some of the disadvantages, if I should list them, is they can be challenging, since it's a quite an unfamiliar way of thinking, of designing your system, an unfamiliar model in general. Versioning of events can also be quite challenging, which is a whole chapter by itself. It's probably a whole talk by itself, by the way. But it's also something that you need to sort of design for, design for versioning, design for upgradability of protocols, etc. And deletion of events, even though that I've said in the beginning that conceptually you should not delete. There might be legal reasons for actually having to do that if a client asks you to. And that can be also challenging. Some techniques might be replacing the events with the tombstones. Actually, so there is a sign that's actually there was an event here, or just delete certain anonymize the events by leaving them in through some sort of tombstone, or other techniques can be sort of using encryption. Encrypt all the fields in the event, for example, and then if the user asks, then simply throw away the key. I just want to briefly mention some around events and time as well, because I think one of the key things here is that events also allows us to have a stable notion of time. Time is one of the hardest things to get right in distributed systems in general. So I personally take all help I can get here. Greg Yagwan once said that modeling events forces you to have a temporal focus on what's going on in the system. Time becomes a crucial factor in the system. And I really believe this is also one of the huge benefits of events, that it forces you to think about time, think about causality, think about progression of state, etc. And event sourcing actually gives us a great tool to model time, because the event here can be a snapshot in time. So a snapshot of what does the world look like right now. And the event ID can be natural index for time, and the event log is our full history. It's, as I said before, it's the database of the past, not just the database of the present. And one really interesting sort of thing when you have such a thing in place is that event sourcing then allows for things like time travel. So what I mean by that is that it can give you tools for doing things like replaying the log for historic debugging. If you want to understand what went wrong and where it went wrong and why it went wrong, you can simply go back and replay the log, bringing you slowly, step by step, up to the point where you are right now. You can also replay the log for auditing. You have bulletproof auditing right into the event log itself. You don't need to sort of do. So duplicate that into some sort of audit database, etc. You have full traceability of what's ever going on in the system. You can also sort of replay the log on failure, as I've already talked about, sort of in the SAD path, bringing a component up really sort of fully up to speed after a failure. Perhaps rehydrate the log on another node, then if needed, if the current node is actually down. And it also allows you to sort of replay the log for replication. For so cloud computing can really gives us tools for having a lot of redundancy in the system, and I think the event logging and event sourcing as a pattern can really help us achieve that through replaying the log. It means you can replay it as many times as you want, bringing replicas up to speed, for a sort of active passive fashion, or in fully active sort of fashion, if your design allows for that. You can even do like funky things like forking the past into multiple universes, or join two distinct paths into one single local present. So the key takeaways here, I mean, if we should try to summarize, is that microservices are really hot, but you should not settle for building microliths. You should go all in, understanding that microservices come in distributed systems. They only make sense, I'd say, in systems, and that microservices also come as systems. You need to view each microservice as a system in itself, with a lot of moving parts. I'd say, in order to really take full advantage of the promise of microservices and go all in on distributed systems and cloud. And in order to do so, I think we have a lot to gain from sort of embracing the reactive principles, reactive systems, defined as reactive manifesto, reactive programming, with things like Akka streams, or RxJava, and these type of newly upcoming approaches like stream processing, like Flink and Spark streaming and things like that. Also embrace events-first domain-driven design as sort of the design tool in order to come up with a design that's actually ready for this new world, with commands and events representing intents and facts, and fully embracing event-driven architecture, event-driven persistence, and in order to do so, you get a stable notion of time, as I've already talked about, that gives you sort of really the bedrock for full reliability, for full availability, traceability, and scalability. So in general, I think this will put you on a path towards being ready for modernizing your monolith, and sort of going all in on microservices. And if you want to learn more, I wrote a little mini book here that's freely available in this bit.ly/reactive-microsystems here, so you can download it for free there if you want to dig in some more. So that's all I had. Victor?
Assuming 1 million events per second, how do you debug that, and how do you monitor that?
Yeah, that's a great question. There are some emerging tools, for doing monitoring in this new world. But in general, I'd say that monitoring companies is really lagging behind. I mean, most traditional APM tools and things like that are not suitable for this new world. Most of the tools that have sort of come out for that are implemented or delivered by the open source community. So I think there's a lot of work to be done here. There are tools like Visual, for example, that I think came out of Netflix, and that can help you a little bit with that, and similar type of tools. Some of them that we are rolling into are monitoring, offering at Lightbend for monitoring Akka and Logom microservices, but I think we have a long way to go as an industry to get full visibility at scale for these type of systems, to be honest.
All right, next question. What is the difference between a fact that has been invalidated by future facts and deleting a fact?
Yeah, I think it is a crucial difference, because if you invalidate an existing fact, that means that the old fact is still there. So if you pair that with event logging, you know why you ended up with the understanding of the world that you actually did, and how you got there, because you can sort of trace your insights and how your knowledge evolved over time, back by just looking at the event log. If you just delete that, all history is lost, that's really. So I think it's a crucial difference here.
Yeah, I mean, I guess you could have acted on this invalidated fact, and you might want to understand why things were done, which you wouldn't necessarily know if. Yeah.
I mean, every fact, usually, at least if you use event sourcing, that means that every fact actually represents a state change that was caused by you doing something, So you have, so while keeping all of the facts in order as they arrived and how your knowledge evolves, it gives you full insight of how and why you ended up where you did. So.
All right, next question. So if we focus on verbs over nouns, wouldn't that lead to conventional procedural design?
Just to some extent, yeah, perhaps. Yeah. I think you might look at it like that, but I mean, so I sort of sense that the guy asking this hints that could be sort of necessarily a bad thing. I don't think that is necessarily a bad thing, but I think understanding how complex systems like distributed systems and systems written for the cloud evolves over time. I think it's crucial to understand how data flows. Most of the value in the system today are in data, and data are usually in motion today instead of at rest. And being able to react quickly to data as it arrives is usually where most of the business value it actually is. More so than in the domain objects mapped to SQL databases. They usually called data at rest. So sort of going all in on actually how this sort of how data flows between systems is usually the best way of capturing business value, at least in my experience.
Okay, and here's another question. With an event log, do you mean to imply that there's a centralized log, or how would you avoid getting a huge bottleneck?
That's a great question. I get that a lot, actually, and the way I would design a system is I would never have a centralized log. I mean, I guess you could design a system like that, but in my opinion, the best way of viewing it or designing it is that by having each service backed by its own event log. Then that it's only events that are relevant to this service that are in the log, that are in the order as they arrive. You make sure that you minimize contention for sort of writing to the log, because it's just you can just use a single writer writing events as they arrive, et cetera, et cetera. I mean, there's a lot of benefits from a design like that. There might be more things to maintain, but if you use in sort of something like Kafka, spinning up more topics is usually not that expensive, and it usually doesn't add that much to the management of the sort of distribution fabric, being Kafka or Kinesis or whatever it is. So I would absolutely recommend going down that route.
Cool. All right, let's see if we have any more questions here. No, I think we're pretty good. So let's see. All right, I think I'm afraid we've run out of time for today. But I'd like to thank you, Jonas, for giving us this informative presentation and some really great answers here to a lot of questions. So
thank you, Victor. Thank you, and I also want to thank ACM for hosting me. It was a lot of fun. Hopefully, a lot of people found it useful.
Yeah, thanks for everybody participating in the webinar today. So this webinar was recorded and available online in a few days at webinar.acm.org. And you can find announcements on upcoming webinars and other ACM activities at learning.acm.org and at acm.org. Also, please fill out our quick survey where you can suggest future topics or speakers, which you should see on your screen. On behalf of the ACM, Jonas Bonér, and myself,